One last integral example I want to do involving the fundamental theorem of calculus for line integrals and the corollary that was involved. Let's evaluate the integral of e to the z over gamma, where gamma is going to be, say, the unit circle. So gamma is going to be, say, the unit circle traveled, say, counterclockwise. And so we could think of a parameterization. We could think of gamma of t as being e to the it, where t goes between 0 and 2 pi. Okay. And so this integral e to the z dz is going to end up being the integral from 0 to 2 pi of e to the, let's see, this is a little strange, but e to the it times the derivative of e to the it, which is I e to the it dt. And so if we want, we could just forget about the context and substitute. And if we substitute, we're going to end up with, let's see, we'd end up with e to the I times 2 pi minus e to the I times 0, right? So if we were to substitute, evaluate everything, this is what we would get. I substituted and did it all in one step. You can write it out if you like. And it turns out that this is going to be e to the, let's see, e to the 2 pi I is just 1. So this is e to the e minus e to the e, which happens to be 0. And so, of course, this integral, looking back, of course, this integral should be 0. This function e to the z is holomorphic. It's, again, an entire function. It's holomorphic over the entire complex plane. Gamma is a piecewise smooth curve. In fact, it's just smooth, right? You don't even have to think about it in terms of any pieces. It's just one piece. It's smooth. And so that means that the integral there should be 0. Okay, and in fact, it is. Everything works out very nicely.